Hello students, welcome back to the lecture series of Mechanical Properties of Fluids. This is lecture 2 of the series. In the first lecture, we discussed about ideal fluid, then we discussed about pressure and the pressure exerted by a liquid cylindrical column. The first topic of today's lecture is atmospheric pressure. Let's start with the definition of atmospheric pressure. So it is defined as weight of air column having unit cross-sectional area that extends from Earth's surface to the top of the atmosphere. So, to find out the atmospheric pressure, let's say at a point O on the surface, as I've shown in the figure, the point O is lying on the surface. We consider a cylindrical column whose cross-sectional area is 1 meter square. The cylindrical column that we have considered must extend from the surface of the Earth up till the top of the atmosphere. Now, to find out the pressure, we just need to calculate the weight of the air in the cylindrical column. And that weight of air will be nothing but pressure due to atmosphere, which is nothing but PO. So, the atmospheric pressure at point O, which we can also write as PO, is nothing but the weight of the air in the cylindrical column drawn from point O up till the top of the atmosphere. The only thing that we should remember is that the area of this cylindrical air column must be 1 meter square. Now, there are some important points that we must remember about the pressure exerted by the atmosphere. The first important point is that the atmospheric pressure is maximum at the sea level, and the atmospheric pressure decreases as altitude increases, which means as we go to some height above the Earth's surface, the atmospheric pressure exerted by the atmosphere on us goes on decreasing. And it is quite evident because let's say we go to a point which is at height h above the Earth's surface. Now, at this point, let us call this point O dash. At this point, if I want to find out the atmospheric pressure acting on me, what I need to do again is draw a cylindrical column, which is extending from my position up till the top of the atmosphere. Up till the top of the atmosphere. So I draw a cylindrical column that extends from my position up till the top of the atmosphere. And the cross-sectional area of this cylindrical column is again 1 meter square. Now we can clearly see that since the size of the cylindrical column is reduced, the air that is enclosed by the cylindrical column has also reduced. And therefore, the weight of the air in this cylindrical column, this new cylindrical column, is lesser. Therefore, the pressure exerted by the air on me at some height will also become lesser. Therefore, as we go to some height, the atmospheric pressure always decreases. Okay. So let's start with the next topic of this lecture, that is pressure variation due to change in depth. To understand this topic in a simple manner, I have drawn a figure on the left-hand side, which consists of a vessel filled with fluid. In that fluid, we have considered a cylindrical column, where the cylindrical column has a cross-sectional area A. There are some notations that we must understand first, where the density of the liquid is given by rho. D1 and D2 are the depths measured from the top of the vessel. If you see in the figure, there is a force F1. It is a downward force exerted by the liquid on the top of the cylindrical column, and the force F1 is acting on the top surface. Then we can see there is a force F2. It is an upward force. It is exerted by the liquid which is below the cylindrical column and is acting on the bottom surface. Now, we know that pressure is force upon area. Therefore, force can be written as pressure times area. Therefore, I can write down F1 is equal to P1 times A, and F2 can be written as P2 times A, where P1 and P2 are nothing but the pressures at depths D1 and D2. Let's move ahead in this derivation. So on the left hand side of the screen, you can see an enlarged view of the liquid column. and I've also shown the forces that are acting on the liquid column. Now we know that the liquid column is stationary. It is not moving anywhere inside the fluid. Therefore, the net force acting on the liquid column is 0, which means I can write down the summation of all forces as 0 acting on the liquid column. Now let us consider downward forces as positive and upward forces as negative. Therefore, what we have is F1 plus mg minus F2 is equal to 0. From this, we can easily write down F2 is equal to F1 plus mg. Now in place of F2, I can write down P2 times A. In place of F1, I can write down P1 times A. And in place of mg, I can just repeat mg. So P2 times A is equal to P1A. We all know that mass is density times volume into G. So let's move further in the calculations. Okay. So what we have is P2A is equal to P1A plus, in place of volume, we can write area times depth into G. And the depth is nothing but D2 minus D1, where D1 is nothing but the depth of the top surface and D2 is nothing but the depth of the bottom surface. So we get P2A is equal to P1A plus rho A D2 minus D1 into G. A gets cancelled from all the places, and finally what we have is P2 is equal to P1 plus rho D2 minus D1 into G, and D2 minus D1 is greater than 0, and we write D2 minus D1 as D, therefore D is greater than 0, and finally what we have is P2 is equal to P1 plus rho G D, and since D is greater than 0, we can write down P2 is greater than P1. Thus it can be clearly seen that as we go to the depths of the fluid, the pressure is going to increase. So basically what we can say is, as we move downwards, as we go to the depths, pressure increases, and amount of increase in pressure is rho GD, where rho is nothing but density of the fluid, G is nothing but gravitational acceleration, and D is nothing but depth by which object moves downwards. So if we have an object which is moving downwards in the liquid and it moves downwards by depth G, then the amount of pressure acting on that object increases by an amount rho G D. Okay, let's start with the next topic of this lecture, that is hydrostatic paradox. Now let's have a look at the statement first. It states that the pressure at the bottom of the vessel does not depend on the shape of the vessel, or we can say that it does not depend, the pressure at the bottom, it does not depend on the amount of liquid inside the vessel. Now to understand this paradox, we have drawn a figure on the left hand side of the screen. In this figure, you can see three vessels of different shapes, but the liquid in all the three vessels is filled up to same height. Now, obviously, what we can see is the weight of liquid in flask 3 is greater than weight of liquid in flask 1, which is greater than weight of liquid in flask 2. But if we measure the pressures at point 1, 2, and 3, we realize that the pressure at point 3 is equal to pressure at point 1 is equal to pressure at point 2. Now this is something different from what we had expected, because our expectation was that the weight in flask 3 is more, therefore the pressure in flask 3 should be the highest, which should be followed by pressure in flask 1, and then the pressure in flask 2 must be the least. But what we are getting as a conclusion is that the pressure in all the 3 flasks at the bottom is same. Now, why does this happen and what is the reason for that? Let us understand. Okay, so let's start with flask number 3. Now you can see some green arrows, and those green arrows are nothing but the components of normal reaction. So the normal reaction I have drawn in the red color, which is exerted by the surface of the flask on the mass of the liquid. And that normal reaction I have divided into 2 components, 2 horizontal and 2 vertical. And if we can see clearly that the normal reactions horizontal component, they cancel each other. The horizontal components of the normal reaction, they cancel each other, and the upward vertical components of the normal reaction, as you can see over here, they are opposing the weight in flask 3. So the vertical component of normal reaction in flask 3, since it is in opposite direction, it will oppose weight. In flask 3, it will oppose weight, and therefore it reduces the force exerted by the weight. So vertical component of normal reaction in flask 3 reduces W3. Now, let's see what is happening in flask 2. Now, in flask 2, the normal reaction, we can see that the horizontal components again cancel each other, but now the vertical components are in downward direction. And therefore, these vertical components of the normal reaction are now increasing W2. So vertical component of normal reaction in flask 2 increase W2. So by using the normal reactions, the W3 is decreased, W2 is increased, and we can say that they are brought at a level equal to W1. So finally, since all the forces become equal, the pressure also becomes equal. So this is the hydrostatic paradox, which basically states that if you are measuring the pressure at the bottom of the vessels, then the pressure at the bottom of the vessels will not be affected by the shape of the vessel or the amount of liquid filled inside the vessel. Also, we can explain this by using the pressure formula that we just saw. So in all the vessels, the depth at which we are measuring the pressure is same. And we know that pressure only varies if the depth varies. So since the depth is same for all the points where we are measuring the pressure at all the points is bound to be same. So this is also an explanation where we can write down, just a minute, yeah. Since all the points 1, 2, 3 are at same depth, they have same pressure. So this is another explanation for the hydrostatic paradox. Sorry, I forgot to mention about the effect of normal reaction in flask 1, but it is not necessary because the normal reaction, as we can see, that they are opposing each other and they directly cancel each other. Therefore, there is no effect of normal reaction on weight 1. So we have seen that in hydrostatic paradox that the pressure at the bottom of the vessel, it is independent of the shape of the vessel and the amount of liquid filled inside the vessel. The pressure at the bottom of the vessel are going to be same for all the vessels if the water in all the vessels is filled up to the same height. So this was the last topic of lecture 2. In the next lecture, we will cover the topics of Pascal law. We will look at some applications of the Pascal law and also have a look at open tube manometer and barometer. Till then, keep studying. Thank you.